I'm going to grab your attention again. Sorry that I stopped talking there for a moment. I know that was very confusing. So yes, it is the end of trimester 2. As I mentioned last week, we are not going to take a final this trimester because I don't think it fits in where we're at. It doesn't make any sense for us to stop so that we can get to take a final since we'll all be back here next Tuesday anyway. And so we'll just keep cruising through. But I do have grades due. So any late work that you have that you are intending to turn in so that you don't have zeros must be turned in this week. I need it by Wednesday, okay? Like if there's some sort of crazy extenuating circumstance, then talk to me. Otherwise, make it in by Wednesday, all right? Because I need time to get it done so that I can start planning and all of that sort of deal. So Wednesday at 4 p.m., that's my deadline for you, okay? I have not yet put in your resonance labs, and I have not yet put in your that balance lab, the mass of the stick, okay? But other than that, I think that everything should be up to date. Oh, and there are a few of you that have just did corrections that haven't gotten corrections back in, okay? So you look like you're confused. Talk to me.
What's the measure of the stick lab?
You were not here, so you need to come do that. We did that last Monday when you were gone. You look confused too, Ian. What's up? Friends, I would really, really appreciate if you could be quiet so that I can hear. Also, it's just respectful. And you might want to know the answer. Go ahead. Yeah. No, the one that you guys did this morning.
Oh,
yeah.
Okay.
Yeah, that one as well. Yes, the one with the marker balance we just talked about, and you did not turn that one in. That is accurate. The resonance lab was the one with the tube and the water and the tuning fork. It was from a while ago. I just haven't graded them yet. Okay? Friends, what did I just ask?
Please be quiet.
Indeed. So can we do it? Thanks. Okay. All right. So any other questions, issues, concerns about that stuff? If you have individual questions or things that you want to check in with me about, then feel free to do that at the end of class. But yeah.
Is there any more assignments for this trial?
No, we are going to do a lab starting tomorrow, but it will not be turned in time for me to grade it for this trimester. So it will be the first big thing for next trimester. Yeah. So if you have everything turned in, then this is just a fun-filled week of physics for you, but no big things to be turned in. There is homework to be done and stuff like that. So, but it's not like there's a big test at the end.
So our final will be like over everything we did this try and inertia and everything.
So the final is really just going to be practice AP stuff, right? Yeah, and so we'll just get there and we'll talk about what it's going to look like when after you're done with all your finals for this try. Does that sound okay? Yeah, I just because it'll be, yeah. Then we can focus on it and not worry about other stuff. Okay. Any other logistics? I like that you're asking questions, and I want you to keep doing that. I just don't want to prolong the process if there aren't questions. Okay. I got an email from Mrs. Naughton this morning, and I wanted to make sure that I didn't forget to tell it to you. This shouldn't be an issue for you, I don't think, but if it is, she says that Friday, March 1st is the official last day that students can sign up to take an AP exam. So I know that most, if not all of you, have signed up for the AP physics exam, which I'm super excited for you for. But if there's something else that you were on the fence about, or there's a AP exam, like if you were going to do English, even though you're not taking the English class or whatever, you have to make sure that you sign up by March 1st, okay? This is like copied and pasted from her email with a changing pronouns. So if I screwed something up, I apologize. If you want to change your testing status from a no to a yes, you need to let her know. That should say you, okay? If you fall into this category, you need to make sure you talk to her to get a registration form and turn in the money again by Friday. So I am just the messenger on this. If you have questions, talk to her. Sound good? Yay! Carbling actually, did something that I was supposed to do. Yay for me. Okay, so we're going to do Moment of Inertia today. We're just going to follow up with a couple of extra questions that we did not get to last time. And then I've got some problems for you to work, and that's going to be our day today. Should be pretty straightforward. As I said, tomorrow we're going to start a lab. This is the big lab. It's a big one. It's a good one. So anyway, something to look forward to for tomorrow. All right. Last time we were together, we were working on this problem, and I couldn't remember. Did we finish this one, or did the bell ring in the middle of it? Do you guys remember?
I think we finished.
We finished both parts A and parts B?
Yeah, we finished both.
No.
Yeah, we did.
But that's what I kind of feel. I don't feel like I remember talking to you guys about part B yet.
It was a Pythagorean
Okay.
theorem.
Yeah, but I don't know that we actually talked about it all the way through, did we? I don't know. All right, so part A, I think we're okay with. So I guess let me rephrase the situation. Why don't you take a look at part B? Because it's been a few days since you've looked at it. So even if you looked at it and understood it and got it on Friday, it can't hurt to spend 2 minutes looking at it again. So a friendly reminder that your friend is creating an abstract sculpture consisting of 3 heavy spheres attached by lightweight rods as shown. The spheres have masses of 1, 1.5, and 1. What is the object's moment of inertia if it's rotated about the axis A? So that was part A. I think we did that, and I think that this is what we found. Is that right? Am I remembering this correctly? Help me get back into my realm. I think that that's right. But then about part B, or in part B, about axis B. So we're taking, let me just kind of get you back into the mental space that we were in. Okay. What's moment of inertia, Miss Carbling? It's been a few days and I don't remember because it sounded scary, right? Moment of inertia just means whether or not something is easy to rotate or difficult to rotate, or to start accelerating or to slow down, okay? That's what we're talking about. We said that when we have moment of inertia, we're talking about both the mass and its distribution about the axis. So that's the key that's different here, is that in A and B, it's the same sculpture. It has the same mass. So if we were just going to drop the thing, okay, we could calculate the force of gravity the same, no big deal. But when we start talking about rotating it, the distribution of that mass matters. Yeah.
What's the unit for moment of inertia?
What is the unit for moment of inertia? It's
Kilogram.
kilogram meters squared. It's kind of one of those whatever units, right? It's uninspired, let's say. It needs some help, but it is what it is. So in A, we've got this thing and it's rotating this way out of the page, right? In this one, the axis goes in here and the thing is spinning along the board. Okay? You with me there? Is that okay? Yeah? So why don't you talk at your tables right now and figure out how you would calculate the moment of inertia for part B, and whether it's going to be the same or different, because I guess that's part of the question too, isn't it? So go ahead and do that. Have a little conversation. Work on it. We'll regroup in just a minute so we can move on. Okie dokie, my friends. Let's get started. So for part B, do you have an answer? Yes. What's your answer?
I got
350 kilogram? Is that what you said?
centimeters squared.
Yeah.
Sorry.
Okay. Do we have people that agree with that? Yeah? I see some people shaking their heads, but I have some people that are like, I don't know. So let's talk it through. Let's go through it and make sure we understand. So we want to add up the total moment of inertia, right? And in this case, because the bars here don't have any mass or have nearly zero mass, we're going to count those as zero. We're just going to add up these masses. So we've got the moment of inertia of mass 1 plus the moment of inertia of mass 2 plus the moment of inertia of mass 3. And how do you find the moment of inertia of a single particle or a point mass? Mass times radius squared. So this is m1 r1 squared plus m2 r2 squared, blah, 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 blah. I get really confused when I start saying blah, blah. I apologize. There we go. What's the radius? What's the distance between the axis of rotation and the mass for mass 1? 0. So that one goes away again. That's nice. mr squared for this one, for mass 2, as this thing spins around, if you think about the circle that it would sweep out, it's 10, right? It's still going to be 10 centimeters away from the axis of rotation. So that's still going to be 1.5 kilograms times 10 centimeters squared. So it looks very similar to part A. Is it just going to be the same thing? Jasmine's saying no, but I'm not sure why. We got the mass for 3 is just 1 kilogram. And then the distance for 3 is not just 10 centimeters, is it? It's 10 root 2. Where are we getting the 10 root 2 from? A squared plus B squared equals C squared, the Pythagorean theorem, right? So this mass, if you put a point here and you measure that distance, and that would swing out like this, right? That radius is going to be 10 root 2 squared. Okay? That's centimeters. Okay? When we add all that together, we get 350?
Yeah.
We agree? My stylist is like, I wrote that already. Okay? So the interesting thing, the thing that we're observing here, is that we have the same object, but it has a different moment of inertia, not depending on where we rotate it. Remember we had the hammer last time, and if we rotated off of one side, we had one moment of inertia. Rotated off the other side, we had a different moment of inertia. This time, it's the same place that we're locating that axis, but it just depends on which way we're rotating it. Okay? So moment of inertia depends on where that axis is and what direction you're spinning it. It's kind of interesting. Okay. Let's see. Oh, yeah. We're going to do this problem next because I like this one a lot. You've seen a picture like this before, so you might say, we've already done this, but we haven't. We've done something very similar to it. I'm going to leave this up here for you to look at for a couple of minutes and to talk about, and then we'll discuss it as a big group in a minute. I'll read it to you just in case it's hard to see from the back. A wheel is composed of 2 pulleys with different radii labeled A and B. So there's one here, A, and then the longer one is B, that are attached to one another so they rotate all together. So it's all one thing that's going to rotate. Each pulley has a string wrapped around it with a weight hanging from it as shown. So this weight is just hanging on the one with radius A and then this one over here with radius B. The pulleys rotate about a horizontal axis in the center, just like that. And I've got this whole thing, and when the wheel is released, it is found to have an angular acceleration that's, now this is where when you get to higher level math and you start doing fun cross products, the whole out of the page thing is going to matter. But for what we really care about today, we're just going to go with it rotates counterclockwise. So counterclockwise means that this whole thing is going to rotate in that direction. Okay? Or I should say, I just gave away the first question. Sorry. It has an angular acceleration, so let's talk about why that's the right answer. Sorry, I just slipped. Sorry about that. It starts out with a velocity of what? 0, right? So its angular velocity is also 0, and it starts moving this way. You with me there? Okay, so if it starts moving that way, it's going to have a moment later a velocity that's in that counterclockwise direction. And if you have 0 as your first velocity, and you've got some counterclockwise velocity as your second, then that means that acceleration has got to be pulling in that direction. Okay, so I gave you that one. Free answer. You're welcome. Counterclockwise. Wait, what? You want me to say it again? With different words, maybe? Okay, let me try one more time. Oh, I don't speak Espanol. Sorry. Nobody wants that. English is the only language that I can fairly effectively communicate in. Yes. All right. So let me say this one more time just to make sure it makes sense to everybody. So that pulley is sitting here, right? It's not moving. So its initial omega is 0. Okay? So we've got, let's write this down. Here we go. So omega naught, or omega 1, is equal to 0 radians per second. And some final omega is, well, it's turning this way. Is that positive or negative when we're talking about angular speed? It's positive, right? So it's got some sort of positive angular velocity. So if we wanted to know the angular acceleration, right? Angular acceleration is equal to, well, I guess we're kind of working backwards here. Omega final minus omega initial divided by time. For this thing to be negative, or to be positive, this one has to be positive as well. Does that make a little more sense? You can say no. It's okay if you say no. I just need a response of some sort.
No, I don't know how. You said like you already know it's turning that way. How do you know it's turning that way?
So it says that it's okay. I was reasoning backwards. Let me try again. Angular acceleration is positive. I know. Yep. So I'm walking you back. Stay with me, Henry. Henry, stay with me so that I can help you. Okay. If you're talking to somebody else, it's really hard for me to help you. Okay. Angular acceleration is counterclockwise. Is that okay? Because it says it right here in the problem. You told me counterclockwise is positive. Is that okay?
Yes.
Okay. So that means that, and I know this definition right here, yeah?
Yeah.
Okay. So I know that this is positive. I know that time has to be positive because it always is. I know that omega initial is 0. What's that?
That's a good explanation right
Good. I'm glad you like it. If this thing's got to be positive, then what does this one have to be? Hot diggity it is. You're right. All right. Third time's a charm. Sometimes it takes a while. It's Monday. Woo! All right. All right. So are we okay there?
Yeah.
Now we understand part A. Yay! Okay. You get to do parts B and C. I'm going to shut my mouth now so I don't give away any more information. Shh, Miss K. All right. I want you to tell me the net torque on the pulley and then which of the or how do the masses of the two weights compare? Go. Let's do it. So part B says, it asks, is the direction of the net torque on the pulley clockwise, counterclockwise, or none? And how do you know?
Counterclockwise.
Counterclockwise. I have a vote for counterclockwise. Do you tell us why you think so, Harrison?
Not really.
Oh, well, I would like you to. Would you please tell us why you think so? Let me rephrase the.
Well, if the acceleration or if the angular acceleration is in counterclockwise direction, then the net torque would be in the same direction.
Why? He knew I was going to say
I
that.
don't know.
You can help him out. We can.
Yeah, Rudy, take over.
Take it away, Rudy. I didn't say anything.
Go ahead, Nick. You've got your hand up.
We'll use that one equation, the rotational acceleration equals the net torque of the moment of inertia. And the moment of inertia is always positive. And so like, once in
It's like it's like A equals F.
Yep. Oh, it's all frozen. You can't even see all the awesome stuff I just wrote. Sorry about that. Yeah, for sure. So the purpose, or one of the purposes of this question, is really to get you to internalize this, right? That it is just like the translational stuff, okay? But that I want you to make sure that you're okay with that because rotation is not something that we like naturally think about. We're used to things moving in straight lines. Like that's what we're used to thinking about. That's our reality, okay? So sometimes this like rotation stuff gets a little bit goofy, but just like we have with A equals F over M, this direction and this direction, the acceleration and the torque have to be in the same direction, okay? It wouldn't make sense for it to be backwards, okay? And moment of inertia doesn't have a direction, so there you go. Okay, part C, this is the big one. But which one's bigger? And how do you know? Who just said obviously A? Who was that? Was that you? You know what I'm going to say, right, Ian? Obviously A, the mass of A, is greater than the mass of B. I didn't say obvious. I want to make that very clear. I'm just picking on you. Do you want to tell us why you're asserting that A is bigger than B?
because the net torque is unequal, and even though B has a greater radius, which would increase its torque, it's accelerating in the counterclockwise direction, so that means A's mass will stay longer. So it'll have a greater torque.
Do you guys understand what he was just saying? Anybody want me to say that again?
Yes.
Yes?
It doesn't
So-
really matter unless, like, this one's going this way. Well, actually, it doesn't matter.
So So well, let me back up. So the torque, which one's bigger, the torque of A or the torque of B?
Because it's,
Why A?
because it's, okay, wait, you're looking for like the way it is.
Yeah.
It's, if A had greater torque, it would be going down, so then it would rotate counterclockwise like it is. If B was bigger, it would be going the other way.
Well, so we have to be careful with this. Would it be possible for these two to be like in equilibrium, or even for one to be, I mean, like, you have to be careful because of the radii, right? Yeah. So if we talked about this in terms of the forces, that's the thing that I really want you to pay attention to, guys. If you talk about it in terms of the forces, there's a lot of conversation here that's really distracting to me. Okay? And I don't care if it's distracting to anybody else. Well, I do actually. I care about the rest of the people in the class. Please stop talking. Okay? If you have something to add, please add it to the conversation. Thank you. So this one's pulling down here, right? This is the force of A. And this one's pulling down here. That's the force of B. But we know that not only does the force, like the force is not really the issue, it's the torque. Torque is force times distance, right? So if we write that down, so we're saying the torque of A has to be bigger than the torque of B, which is really the force of A times the radius for A has to be bigger than the force for B times the radius for B. Okay? We know that the radius for A is little. So that's not going to get you where you need to go. Okay? But it's got to be the force that's bigger to give you that acceleration, that angular acceleration to get it to spin. Okay? We good? All right. I feel like I made myself a note that this problem really should have gone earlier in our experience, but it's good. It's good conversation. We're gonna go back to another ranking task. This one is more on the order of talking about moment of inertia. Just FYI, here it comes. All of the moment of inertia problems we've done so far have just been masses, point masses. And now we're venturing into the realm of non-point masses. Yay! It gets more exciting. All right, so here we go. We've got 3 flat objects. We've got a circular ring, a circular disc, and a square loop. They all have the same mass and the same outer dimension. The circular objects have diameters of 2r. The square loop has a side of 2r. The small circle at the center of each figure represents the axis of rotation. The axis of rotation passes through the center of the mass and is perpendicular to the plane. So it's going into the page or into the board. Okay? So this thing is going to spin this way, or it could go the other way as well. The question asks you to rank the moment of inertia of these objects about its axis of rotation. Go. Feel free to get a whiteboard. Yes, you're welcome to. All right. So what did you say?
Cows make noise. I'll
Yeah.
tell you after.
The ones
Okay. All right, friends, let me see your answers. Show me some answers. All right. So you can put your boards down and close your mouse real quick. So I see an order that's written down on most of the boards, but I see some equal signs and some greater than signs, and they're all in different spots. So what I read into that as a physics teacher is we're not really sure, but that's our gut feeling. So I want to figure this out. I'm going to start by looking at just A and B. Can we start there?
Yeah.
Let's leave the square out of this business. How do the moments of inertia of A and B compare? So the question is A, oops, let me write this in a nice formal physicsy sort of way. The moment of inertia of A is equal to the moment of inertia of B. The moment of inertia of A is greater than the moment of inertia of B, or the alternative would be AI is less than AB. or IB, excuse me. Who wants to advocate for one of those and, move us forward in this process?
He's greater than
AI is greater than IB.
yeah.
IA is greater than IB. I'm speaking very well today. This is the one you're advocating for?
Yeah.
Yeah? Do you want to tell us why?
Yeah, sure.
Awesome.
So, moment of inertia is the mass times the radius. So, well, not quite. Yeah, radius squared.
Okay, let's just say it like it is.
Yeah, anyways.
For sure, yep.
And the concept still applies. In A, all the mass is concentrated on the ring around the edge.
Okay.
And so, the radius for all of the mass will be higher overall.
Okay.
Whereas in B, there's more of the mass towards the center. And they have the same mass overall, but more of the mass is towards the center, so the radius will be smaller in that area. So the overall moment of inertia will be smaller.
Okay. So so that was good explanation. Thank you for that. I'm gonna take it one step, I'm gonna back it up a step, just to make sure that we're all okay. So remember this problem that we did a couple of minutes ago, maybe a few minutes ago? When we found the moment of inertia, we had to add up the pieces, right? Add up the moment of inertia here plus there, and then we can get it. We can do the same thing in this problem. So we've got lots and lots of little pieces of mass. Like in A, we've got one here, and we've got one here, we've got one here. Let's look at those three pieces, okay? And we can look at three pieces in B as well. Maybe we've got one there, but then we've got one here, maybe we've got one right here. Does that make sense? And so these three pieces on A have the same mass as the three pieces in B. Is that okay? I'm taking 3 chunks, cutting it up into 100 chunks, and I'm just taking 3 of them. Okay? If I'm going to calculate the moment of inertia for this chunk here, they're all going to have the same radius. Does that make sense? So this would be 3 times mass times radius squared, okay? Where R is that radius of the circle. On this one, that first one is the mass times the radius squared. But the second one has a radius that's definitely smaller, right? R2 squared. And then the radius for that third one is almost nothing. That one's almost 0. Kate, you're looking perplexed. Can you vocalize
Well,
your face?
You said you just broke it up into 100 pieces. Why couldn't you just you chose those specific pieces because the pieces would be different, but then if you just move them to the outside, they'd still be the same as the A. So
it's true, but there would still be pieces in here. So this is all the mass is all distributed all through this.
Wait, there's
right?
nothing in the ring?
No.
All of the mass is concentrated at the outside. Does that make sense, Courtney?
Yeah, kind of forgot what a ring was.
Okay.
help me with you.
Okay, so does that answer your question?
Yes, I guess.
Harrison, go ahead.
Doesn't that not also account for the fact that it's less concentrated? The spots you chose on each of them in B, the little areas will.
Yeah, so I was just trying to point particles, right?
Okay.
Yeah, just little pieces where all of these pieces are the same as all of those pieces. You're right.
Okay.
Yes, they're not drawn to scale.
Okay.
Is that fair?
Yeah.
Fair question. Yes, I was just trying to pick 3 little pieces here and 3 little pieces in here.
Oh,
Yes.
I didn't know if that was what.
Yes. Does that maybe that wasn't very clear in the way that I said it. We better now?
Wait, so
Go ahead, Henry. Go
say
ahead.
that one more time, the radiuses are all the same.
So if I take
Right, yeah, that's what I'm talking
So Henry, if I just take little tiny chunks, right, of the same mass, I cut up the mass of this into 100 pieces that are equal mass, and I cut this up into 100 pieces that are equal mass. Does that make sense? Okay? Any 3 pieces that I pick in A will all have a radius of big R away from the axis of rotation. Is that okay?
Because there's nothing in the center.
Because there's nothing in the middle.
I remember what a ring is.
Okay.
I'm trying to help.
No, so are you okay?
Yeah.
So if I take 3 little chunks again the same mass, okay, but I pick one in B that's way outside. I pick another one that's kind of in the middle, and another one that's really close in. The moment of inertia of this one that's way out on the edge is going to be much higher because the radius is much higher. How are we doing? Are we okay? Okay, so if I add up all of the little 100 pieces here, they're not going to have the same moment of inertia, each one of them, or the sum of them, as compared to this, because these ones are all really far from the axis. How are we doing? You okay? Yeah? Okay. So I think we can say with certainty that the moment of inertia for A is greater than the moment of inertia for B. Is that okay? Okay. So A is bigger than B, so we're going to go ahead and mark that. And then we have to deal with A and C. A and C look a lot more similar, perhaps, in that they're both kind of ring-esque. They've all got their mass on the outside. So does that mean that they've got the same moment of inertia in both cases? Gunnar is shaking his head with fervor back there. Why?
Because with C, because it's a square,
Uh-huh.
corners will have a bigger radius than in A.
Yeah. So if I take, again, any little chunk in A, they're all going to be R away, right? And if I take this chunk here, that's going to be R away. I could even take two that are exactly that R away. But if I take this part right in the middle, that's going to be more than R away, right? Yeah. And so the further away it is, the bigger the moment of inertia is. So which one has a bigger moment of inertia, C or A? C does, certainly. Oop, there we go. Okay. So they're both, or all three of them are different moment of inertias. Okay. Conceptually, does this make sense? So in my AP physics with calculus class, after we do this problem, then we do the calculus and we just add them up, right? It's just a sum. That's literally all I'm doing here. It's just a little integral to add up all of the pieces. Add up all the pieces, add up all the pieces. We're not going to do that in here because that's beyond the scope of this course. If you want to see it, I can show it to you sometime. It's not that hard. But for our purposes, I am going to show you that it does happen and it does work out and it makes some kind of funny equations. Okay? So for example, the moment of inertia of a slender rod with an axis through the center, okay? We're just taking all of those little bits one at a time. So there's one right here, and then there's one right here, and then there's one right here. Add them all up because the radius changes each time, okay? It ends up that the moment of inertia of that thing is actually 1/12 the mass times the radius, or the length of it, squared. Okay. You take that same slender rod and you spin it around one of the ends, and holy cow, it's going to increase that moment of inertia, right? Because now this end is really far from the axis of rotation. And so instead, when you add it all up, you're going to get 1/3. Okay? And then you can go through with these, and you've got this little rectangular plane. You've got this thin-walled hollow cylinder. You've got a solid cylinder, a hollow cylinder, all these different things. Okay? I want to show this to you so that you're aware of it, so that you're familiar with it, and that it is a thing that you've seen. You absolutely do not have to have these memorized, okay? That is not a thing. You do not have to have them memorized, but what you do need to know is that you might see something like this on a test, okay? Where it would say, there's a, blah, blah, blah that can be approximated to a rod with an axis through one end, and the moment of inertia is 1/3 ml squared, okay? So you don't have to memorize it. You don't have to know where it comes from at all. That's not a thing. But not being scared of it is the thing that I want you to be, I want you to feel good about, right? Oh, okay. I know that some calculus people can do that. I'm a calculus person or I'm not. It doesn't matter. But I just know that I can use this. Okay? What we're going to do for the rest of the period, I've got 3 problems that involve some fun moments of inertia and some interesting torque and some kinematics. It's kind of mashed all together, okay? And I've got them printed out. I'm going to hand them to you. Also on the back is this same chart, okay? So you have your very own copy. Yay! Okay, again, you don't have this memorized, but it's there for you. I'm going to give you some time to work. You've got about 10 minutes, I think, to work. So I want you to actually spend some time enjoying some physics, all right? I'll hand them out to you in just a second. Hold on.
I like that.